In this lecture, we'll discuss about the charge pump and the loop dynamics of type 2 PLL. First, we'll discuss about the charge pump. Okay. So, what is a charge pump? Charge pump is basically, a circuit which is used to convert whatever the phase difference that we have got, right? QA and QB, the information that we have got, that QA and QB, right? We have seen that if the phase of A leads the phase of B, then QA, the average value of QA is always higher than the B, or B will always be 0. Similarly, if the frequency of A is higher than B, then still the QA will have a lot of pulses. Okay, so this digital pulse we want to convert into analog voltage, because ultimately we'll apply that voltage to the VCO, just like we have discussed in case of the type 1 PLL. So we can see here that the omega A is higher than omega B. So what I am supposed to do now is I am supposed to increase the oscillation frequency of VCO, and this we can do by increasing the control voltage. So what we want to do now is that if there are a lot of high pulses for QA, then I should increase the control voltage of the VCO. So this is what will do with the charge pump. So charge pump use a basic mechanism of basically, charge pump is nothing but a current source. Okay, so suppose if I have a current source here, okay, from VDD, and if I, if I pump that current in a capacitor, let's call it as CP, then we want to see what is the behavior of the voltage of this one. Okay, so let's call it as, maybe let's V out. Okay, so I want to know if I pump a constant current I in a P, how will this voltage looks like. Okay, so we know that the charge stored in a capacitor Q is equal to C into V, and we know that if I differentiate this Q, and this T is dV by dt, and this is nothing but the current I, and this is C dV dt. Okay, or I can write it as the voltage dV is integration of I dt, or in this case this is IP, so IP dt. Okay, so basically the voltage, if I integrate both sides, sorry, so then the voltage V out will be nothing but the integration of the IP dt. So basically it will be an integral function, right? This we generally use even in op-amps. When we want to get an integrator, we use the similar kind of expressions. Okay, we try to generate a constant current source and we pump it in the capacitor. So basically the current that so basically the voltage that is getting developed across this capacitor CP is the integration, or it is, I can say that as we pump this current slowly, this voltage, because my I is constant, so basically the voltage is going to increase slowly in an integral way, something like this. Okay, because if this I is constant, so this IP comes into outside, and this integration of dt, so it is basically IPT. Okay, so with the passes of time, the voltage is going to increase linearly. Okay, so we'll come back to these equations eventually more, as we discuss the loop dynamics of the PLL. Okay, so similarly, if I, instead of pumping in, so let's break this one, let's break this part, so that I don't have any more connections now. Okay, so instead of pumping the current in the capacitor, okay, so if I again pump the current out, actually pump the charge out basically from the capacitor, right? Okay. So initially maybe it has some voltage and some charge is stored, and if I pump this charge out again with a constant current IP, we'll see that the in this case with time, again the integration is happening but in a reverse way, and the V out, right, if I plot the V out, the V out is going to linearly decrease. So this is pumping out the charge. Okay, the same thing is going to happen. Okay, so basically what we can learn from this is that you know, by using a charge pump, we can either you know, pump the current in the capacitor and increase the voltage, or we can pump it out from the capacitor and decrease the voltage. Okay, and if I even disconnect this one, okay, if I disconnect this one, then what is going to happen is whatever the voltage that it has developed, right, it is supposed to maintain that. Okay, it is supposed to maintain that, and you know, suppose I have pumped in some charges and it has reached to maybe 1 volt. So this 1 volt is supposed to be stored in this capacitor. Okay, so this way, by this we can, we can store this voltage, and this voltage can be used to supply to the VCO. So even if there is no activity going on, still this voltage can be stored here and it can be supplied to the VCO. So that is the beauty of the charge pump based PLL. Okay, and we'll see this one more elaborate. Okay, so I'll come to this point eventually. Okay, so now what we are going to do is that we are going to, go back to our this one, the phase detector, and we will use this QA and QB to, turn on the current source either in the up one or in the down one. Okay, so this QA, there's a switch here, and QA will be used to turn on and off this switch, and there is this down switch. Okay, and QB will be used to turn on and off this, the lower switch. Okay, so if my QA is high, this is going to, this is going to turn on. Okay, and the IP is going to flow here, and slowly the voltage of this capacitor is going to ramp up. Okay, similarly, if my QB is high, this switch is going to be turned on, and the capacitor voltage is going to drain out and the voltage will reduce. Okay, so and we'll apply this voltage in the VCO. Okay, so let's see the waveforms. Okay, let's see the waveforms, that how it's it does the integration. Let's see some example. So consider this example. Okay, so this is phi A, phi B, and QA and QB. So when this so let's analyze this voltage V out. Okay, so let's draw the waveform of this V out. So when this QA is high, okay, so when the QA is high, so slowly there will be a ramp voltage. Okay, I should set it till this point. Okay, my voltage is going to ramp up. Okay, and of course during this period right, there will be a small time duration where both QA and QB is on. So during that period, the whole of this current, both of them are on, so this whole current is going to go throughout like that from the VDD to the ground, and the capacitor is neither going to be charged nor is going to be discharged. so it's going to maintain itself. Okay, of course, in the real sense, there may be a small mismatch between this IP and this IP. This current source and current sink may not be exactly equal, so there may be a small error, right, depending upon how much is the difference. Okay, but the attempt is generally meant to make these two as same as possible. Okay, so now once both of the switch is off, then the charge is going to maintain, right, in the capacitor. And similarly, next time when QA is high again, okay, so my this capacitor voltage is again going to increase till this point. Okay, till this point when both of them are on. Okay, like that. So so you can see that there will be a you know, ramping of the V out. The vice versa is going to happen if, you know, if my QB is high whereas the QA is low, then the voltage V out is going to go down. So now as the voltage goes up, V out goes up. So, and if we are applying this voltage to the VCO, so what it's going to tell is that makes the VCO oscillate faster. Okay, so that means because because what is happening is now the frequency of A is much higher, or the phase of A is higher. Okay, and now the only way to log the phase or the frequency may be by increasing the frequency of the VCO. Okay. Okay, so let's try to draw the complete diagram of a charge pump PLL. Okay, so instead of calling this output, now let's call it as the control voltage. So now this will be the V control, and now what we'll do is we'll apply this control voltage to the, you know, VCO. And of course, time being, we are not using any divider, so we are going to connect this output of the VCO to this to the V. Okay, so finally this will be my V out. Okay, so as I was mentioning, if the frequency of A is higher, okay, let's call it as now V in. If the frequency of A is higher, or frequency of this, again this A and B, frequency of A is higher or the V in is higher, that means my QA, we know that will have more pulses and this will turn on, and this will increase the control voltage, and it will tell the VCO to oscillate faster, and of course it will oscillate faster, and it tries to, you know, I should say that match with the frequency of A. Okay. Similarly, if my you know, the frequency of B is much higher, that means I'll have more pulses here. It will be turning on more times, and then what will happen is it will drain out, and the control voltage is coming to come down, and the VCO frequency also will come down, and it will try to match A. So this is going to happen when both the if there is a difference in the frequency as well as difference in the phase. So this is what we have seen, right, last time also, that even if there's a difference in the phase, this is going to become high. So so what is going to happen is, if there's a difference, if this is leading the phase, that means this is going to turn on, and momentarily the frequency of the VCO is going to become higher. Okay, and this to the it'll try to match the phase, and once the phase is matched, then what will happen is, of course, so a time will come when, you know, the you know, because this frequency is much faster, so this also will become high, so it will come down, and finally it will settle to the voltage where it is oscillating at that particular frequency, and finally these two phase will be matched. So basically, even if there's a phase mismatch, momentarily the VCO may ramp up the frequency, but then again it comes down to match the phase error as well. Okay, so One very important point of the charge pump based PLL is that, see, this phase detector is able to detect who is leading and who is lagging. Okay, so basically in this case we will see that the phase error between A and B can be zero, right? So in type 1 PLL we need a phase error to get some control voltage, right? But in this case, because I have this capacitor can store the charge and it can get a voltage, right? Control voltage, and for that we can make this phase error between this A and B can be zero. So even if the phase error between A and B is zero, because this capacitor will maintain some voltage, and that voltage can be that control voltage will be able to oscillate the BCO at a that particular frequency, as a result of which in this case we can make the the phase error between A and B zero. So we'll when we'll try to understand this mathematically, we'll also see from the mathematical perspective why it is happening. Okay, I think the concept will be more clear as we do the simulation, and I'll simulate this whole circuit and show you how it is working. But before we go to the simulation, let's try to little bit understand the loop dynamics mathematically. Just like we have tried to understand in the type 1 PLL, we should also try to understand the loop dynamics of the type 2 PLL, and see whether whatever the concept that we have, you know, try to develop till now, whether it actually works or there is some problem in that. Okay, so we should be able to because it's a closed loop system. If it is an open loop system, it's going to work, but because we are going for a closed loop system, so there is a high possibility that there can be an instability issues, right? So we need to make sure that there is no instability issue. Okay, so let's try to a little bit understand the loop dynamics of type 2 PLL. Okay, loop. So we have understood the basic operating principle of the type 2 PLL. Now we'll try to understand the the loop dynamics of the type 2 PLL. Okay. Okay. So this is my let's this is the phi A. Let's call it as this is phi A. Okay. And for phi B, I'll have the almost the same frequency, but with a with a shifted version of this one. Okay, so this is my phi B. Okay, and because of which it is going to produce a signal QA, and in this case QB will always be 0. Okay, so I will not be drawing the QB. The clock edge of phi A is coming before phi B, so only the phi A signal will be high sometimes, whereas the phi B will always be 0. So that means this switch is going to be always off. Okay, so let me draw the QA. Okay, so this is my QA signal, and of course because whenever the QA is turned on, IP will be on, so the signal IP will have the same waveform like QA. Okay, so if I call the current flowing inside this capacitor, of course this is high impedance, no current will flow. Okay, so it's just the voltage that will control. So generally the input impedance of the VCO is very high. Yeah, you can consider it to be infinite. Okay, so when we implement it, is basically the voltage goes to the gate of a MOSFET. Okay, so if I call this current flowing here inside this capacitor to be IT, then the waveform of this IT will be same as QA, because only here the QA is turned on. So whenever these turn on, so I can see this IP current. So let me draw it. So this is just a copy pasted version of QA. This is IT. The current flowing to the capacitor, I should say, and of course this value, that this is the current that is flowing is IP, okay, in the positive direction, because this is going this side into the capacitor, okay. So whenever QA is on, so this is on and these current pulses are going, okay. So now with this I can try to plot the voltage of the control voltage, PCO control voltage, okay. So it will look something like this. So the control voltage will slowly ramp up, okay. Okay, so yeah, so there is a ramping of the control voltage that is happening, okay. So now what we like to do is that we like to quantify this one, and we'll try to write an equation for this. So if you see here, we have the capacitor CP, okay, and we are a current IT is flowing to the capacitor, and basically we want to know what is the control voltage, okay. So now we know this equation that the voltage in a capacitor is the integration of the IT and DT, okay. So this is from the basic equation of the charging phenomena of a capacitor that we have discussed before as well, okay. So now I need to find out this IT. So now if you find out this IT, it is basically this IT is just on, and this on value is equal to IP, and it depends upon what is the phase difference between this QA and QB, okay. So if I quantify this phase difference between QA and QB to be pi, delta pi, okay. So this is delta pi, okay. So where delta pi is equal to phi A minus phi B, okay. So now in a cycle, in a periodic cycle of 2 pi, only for a delta pi amount the IP is on, okay. So in a cycle of 2 pi, it is on only for IP. See, if this IT would have been on, right, constant, like constantly on, if this is on, then the complete, this IT would have been like this IP, right? And the integration would have been very simple. I would have just wrote it down something like this. It would have been 1 by CP integration of IP into DT. But now in this cycle you can see that it is on only for a fraction of delta pi by 2 pi, okay. So only a fraction, the fraction it is on, we can say that it is not IP, so it is on only for, so the integration, this is valid, we are just integrating for a period of only delta pi by 2 pi into IP dt, okay. Of course IP and 2 pi are constant, so I can just bring it out, 1 by 2 pi Cp, and this is, I can write it as IP and integration of delta pi t. And of course this delta pi can be a time variation, and the control can also vary with time, okay. So I cannot bring it out of the integration, okay. It can vary with time, okay. So now we have this expression. Therefore the S domain version of this one will be, if I convert this V control into the S domain version, or the Laplace transform of this one, becomes IP by 2 pi Cp, and this is delta pi S, okay. So therefore we count S by the delta pi S is given by, sorry, so here there will be delta pi by S because of this integral. Okay, so will be given by IP by 2 pi Cp into S. Okay, so this is the expression or the relationship between the V control and the phase difference. So this is the equation which governs the charge pump and the phase detector. Okay, so for a phi s, or for a difference of phi, okay, the control voltage, the variation in the control voltage can be given as IP, which is the charge pump current, 2 pi into CPS. Okay, so now with this, we will be able to get the S domain equation of the type 2 PLL. So this is the, let's focus on the model of the type 2 PLL. So the charge pump and the phase detector and the charge pump can be, you know, expressed by this IP by 2 pi Cp into S, and the VCO, we know that it is nothing but the KVCO by S. Okay, so this is the I should say that this is the loop of the charge pump PLL. So this is my, again, the phi in. Again, let me call it as the change in the phi in, phi out the change. Okay, and so like let's call it as V cont. Okay, control voltage change. Okay, and of course this is plus, this is minus, this is plus. Okay, yeah, so this is the so this is the model of the type 2 PLL. So let's try to find out the open loop transfer function. So if I try to find out the open loop transfer function, is basically the multiplication of this and this, so which is IP by 2 pi Cp into S into KVCO by S. Or if I just combine it, it is something like IP KVCO 2 pi Cp into S square. So now if you see, this system has a two pole in the origin. The open loop transfer function has a two pole on the origin. So now because of having two pole in the origin, this system is going to become unstable. Okay, so this system is going to become unstable, because if I try to draw the open loop transfer function of this one, this is what I'm going to get. So this is my HS open. Okay, this is the magnitude. If I try to plot the magnitude and the the phase, okay, so the there will be a roll off because of the two poles on the origin. There will be a roll off of minus 40 dB per decade. Okay, and if you see the phase, it's going to be, if you see the phase, it's going to be minus 180 degree, because it's a two pole, right? The two pole is going to lag the phase by minus 180 degree. Okay, so this is my HS open. This is the angle of so because of which, right, at this point we can see that the at unity gain frequency, right, there is a phase shift of 180 degree. So what it means is that, see, we have a negative feedback system, and this transfer function, or the open loop transfer function of this one, is shifting the phase by 180 degree. So that means what it's going to do is that the total will be at 360 degree, and because of which the system is going to oscillate at this point, which is the unity gain frequency, UGB. So at this frequency it is going to oscillate. Okay, so this is the problem with this one. Okay, this is the problem with the type 2 PLL. This is an unstable system as the open loop transfer function has two poles in the origin. Okay, so to make the loop stable, we are going to introduce a 0. So by introduction of a 0, basically what we are going to do is that, see, if you see the phase response, so we have a two poles in the origin and it is rolling off. But if we can introduce a 0 something here, then what will happen is there will be, it will reduce and from minus 40 dB to minus 20 dB per decade, and there also will be increase in the phase, because the 0 is going to do the phase leading, and of course towards the infinite frequency this will become minus 90, and as a result of phase margin, of course at the unity gain frequency it will be high. Okay, so this is the basic idea. So we are adding RP for introducing a 0. Okay, so now if I rewrite the expression again, so if I have my RP, so I have my CP and I have my RP, and of course an IT current is flowing. Okay, so the potential developed V cont, now we can write it as V cont. It becomes, so the RP into the current IT, and of course we have the integral of IT dt 1 by CP. Okay, of course this also varies with time, so implies my V cont T will become, so we know that this IT we have written as IP by 2 pi into delta phi t into RP plus 1 by CP. Again, this is, we are substituting it by delta pi t by 2 pi into IP dt. Okay, and of course if we take the S domain like the one that we have done previously, Laplace transform, there the constant values comes out. Okay, so the IP by 2 pi is going to come outside, and of course in this case we can take it common because this is also going to come outside from here. So then it becomes into RP plus 1 by the integration becomes S into CP. Okay, and of course we have the delta phi S. Okay, so therefore my new equation is going to become V cont by S. So we count S by delta phi S is going to become IP by 2 pi RP plus 1 by S CP. Okay. Okay. So now let's try to get the model now with a 0. The phase detector and the charge form is going to look like IP by 2 pi into RP plus 1 by SCP. Okay, so this one, and of course we have the VCO, which is KVCO by S, and this comes back. So we have the control. Okay, so therefore my now the open loop is going to become this one, of course, IP into 2 pi RP plus 1 by SCP into KVCO by S. Okay, so now what we are going to have is, of course, we still have two poles at the origin, but at the same time we have a 0 here. So what we'll have is we have the IP to pi, of course the KVCO we can bring it here, and the expression it becomes S square CP. Okay, and here we are going to have S into RP CP, or we can just write the CP here as well. Okay, yeah, so I have a 0, two poles at the origin, at the same time I have a 0 at RP CP. Okay, so now if I try to plot the again the same transfer functions, the magnitude as well as the the phase of the HS open loop. Okay, so this is my magnitude, and if I try to product phase as well, with a frequency, so yes, I have two poles at the origin, so it will start rolling off as minus 40 dB per decade, but then there will be a 0, and there will be a 0 here. Okay, and this 0, it is omega z, and we have seen that omega z, the 0 is given by 1 by RP CP. Okay, from this equation. Okay, and if it's the phase, so it starts with minus 180, and if I call this as 0 and this is as minus 90, okay, so at this point we know that there will be a phase shift of 45 degrees, so there will be minus 135, and eventually it is going to become something like this. So this is the phase plot, and if we try to see the phase margin here, okay, so this is the phase margin. So we can get a very good phase margin here at the uh, unity gain frequency. Okay, so in the next lecture, we will see how to design the type 2 PLL in LTSpice, and also we'll try to verify whatever the concepts that we have learned. Okay, so we'll see how by adding just a capacitor, it is an unstable system, whereas by adding this resistance, we can see a stable system with a good phase margin. Okay, and of course, this doesn't finish the design of the PLL. There are some more issues are still there that we need to take care of. But this will be more clear first if we first do the simulation in LTSpice. So let's design the PLL in LTSpice in the next lecture.